This was one of the requested ones that you guys sent me an email about. It was number 21. It shows the drawing of a uniform horizontal beam attached to a vertical wall by a frictionless hinge and supported from below at an angle of 39 degrees by a brace. And then they tell you that the weight of the beam is 340 newtons, and because the beam is uniform length, the weight is acting exactly in the middle. There's three additional forces that keep the beam in equilibrium. The brace applies a force P, 39 degrees, and they tell us that the hinge applies both a horizontal and a vertical force, and they want us to find out what P, H, and V are. So this is an equilibrium problem, so we look at some of our units. We look at we want to break up the P. Keep in mind that we're going to have to probably break it up into its X and Y's component. To start off with, we look at one of our equilibrium equations. We usually start off with net torque. We pick a reference point where we can eliminate the most amount of forces. So I picked where the H and V were located. I could have picked where the Px and P, where P was acting, so it could cancel it out. You always want to pick the reference point where it can cancel out the most amount of forces, so either one would have worked. So the net torque created, H and V are not going to create a net torque. So the net torque created, we don't know the length of the beam, but it turns out it doesn't matter. We're going to assume the beam has the length of L. So it will be negative 340, negative because the 340 is going to cause a clockwise torque. It will be negative 340 times L over 2 plus whatever Py is, the y component of P, times the length. We cancel out the L's and we divide 340 by 2, and we get 0 is equal to negative 170 plus Py. So Py ends up being 170, but again, they don't really want us to find Py, they want us to find P, but once we know, since they give us the angle and we just found for Py, we can actually calculate what P is using our trig. So we say sine of 39 is equal to the opposite Py over the hypotenuse P, and then we rearrange the equation to solve for the hypotenuse P, and we find that P is about 270.13 newtons. To find the other forces, we can redo the torque equation, except just switch where our reference point is and solve for V. Or we can use our net force equations. For do the net force equations, we want to find the component Px. So again, we use trig, and we find out that Px is equal to 209.33 newtons. Using that, we also know that everything is in equilibrium, so the net force in the x has to equal 0. So we look at all the forces acting in the x, which is pretty much just the Px component, and the h, which is negative because we put it drawing to the left. I'm pretty sure it's going to the left. If I'm wrong, I'm just going to get a negative answer, which means it should have been pointing to the right. Plug in what we know for Px, so 0 is equal to 209.33 minus h, which means h has to equal 209.33 newtons to the left. And then to find the last unknown, we use the net force in the y is equal to 0 because of equilibrium. And we have three forces in the y. We have V, we have the weight, and we have the Py, which we calculated was 170, kind of got cut off this right there. And when we solve it, we find out that V is equal to 170 newtons. And then we have our values for P, V, H, and P. P is acting at an angle, H is pointing to the left, V is pointing up, and the magnitudes are all calculated there.